Hello, this is David. Welcome to Linda Allen, Chapter 3, Putting Value at Risk to Work. And just like the previous Chapter 2, this is a well-seasoned reading in the FRM syllabus, having been in the syllabus for over a decade. And it primarily concerns value at risk. So this is one of the key chapters in Part 1 that is about value at risk, its strengths and weaknesses, and the various approaches, with an emphasis on what Linda Allen calls the delta normal approach. And that is a specific class of the parametric or analytical approach to value at risk. So we will take a look at this. And the first learning objective is explain and give examples of linear and nonlinear derivatives. And so this is a key frame in the chapter, this idea of linear derivative versus nonlinear derivative. And so a linear derivative is one in which the relationship between the derivative and the underlying pricing factor is linear. It does not need to be one for one, but the transmission parameter or delta needs to be constant for all levels of the underlying factor. And so I would just highlight that aspect of the definition here in Linda Allen. Right? The definition of a linear derivative is one in which the delta is constant, and a nonlinear derivative has a delta that is not constant. You may recall in the stock, so this is really a stock option class terminology, and if the delta is constant, then the gamma is zero. So this is another way we could say this, is that the linear derivative is one where the gamma is approximately zero, and a nonlinear derivative would have a gamma that is non-zero. So related to this idea is that all assets are effectively locally linear, and I've highlighted that. And we're looking at the stock option context, but it applies all the same to the bond asset class context, right? When we study value at risk and risk measurement, at the end of the day, the two asset classes that we focus on in the FRM as foundational or as platforms for learning, I think it's safe to say, are equity and stock options. And then in the case of bonds, it's the duration convexity frame, and they are closely related. They are actually manifestations of the same Taylor series that comes up in a later slide. But the key idea here is that all assets are effectively locally linear, and this applies to option delta in the same way that it applies to bond duration, right? So on the left, I have call price versus stock price, right? This is the familiar nonlinear relationship between the value of an option and the underlying stock price. And over on the right, I have the delta of that same one-year call option. And we can see here the delta is not constant. So this is meeting this definition. The stock option here, this is an illustration of that definition of a nonlinear derivative because the delta itself is not constant. This delta here maps to this by being the slope, right, of the line that's a bad line point of tangency. But if I take a point of tangency, right, at each given point there's a line that doesn't cut through this chart, but actually just hits it on the point of tangency, and the slope of that line is the delta, right? So we start down here, that tangent line has a slope of pretty much close to zero, and then it gets steepest here in the middle at the money. No, or actually that's not right, sorry. It gets increasingly steeper, right, as the underlying stock price increases. So we see the delta increasing, and the delta itself is not increasing in a linear fashion. However, but by locally linear, what Linda Allen correctly and importantly means is that linear approximation, right, although the relationship here is clearly nonlinear, And just below this, I'm gonna sort of not awkwardly sketch the corresponding, and it should be familiar, price yield relationship between for a bond, right? We plot the price on the y-axis for the bond, just like we're plotting value here. And as the yield increases, we know that price decreases, but also this is nonlinear. So that duration or dollar duration here for the bond, that is also the slope of the tangent line, is changing as this underlying factor changes. But what we do in risk measurement, of course, is we'll use the delta to approximate the change in the risk, right? We'll say if we're here at the money and that tangent line has a slope, and we'll use that delta as an estimate, and we can see visually that the greater the shock to the factor, the more there is a mispricing, right? But if we're in here at a small shock to the stock price, you can see the mispricing is not huge. Just like if I take dollar duration is that slope of the tangent line or the first derivative, right? The mispricing, if we just rely on that first partial derivative, the mispricing becomes greater as we increase the shock. But for small changes to this underlying risk factor, which is here is the yield to maturity, the mispricing is not great, just like it's not great here. That's the importance of locally linear. So locally linear means it's generally okay to approximate the change with a small shock to the risk factor. And so for a linear derivative, the price of the derivative is a linear function of the underlying asset. The key is that the transmission parameter is constant and is not a function of the level of the underlying factor. Our classic example here of a linear derivative, of course, is a futures contract. The next learning objective will ask us to define and calculate VaR for linear derivatives, and by definition, the transmission parameter is constant. Therefore, in the case of a linear derivative, VaR scales directly with the underlying risk factor. So when we the linear derivative makes life very easy for us. The VaR of the linear derivative is equal to the delta times the VaR of the underlying risk factor, right? The VaR is a direct linear function of the underlying risk factor. And so, for example, in the case of an S&P 500 futures contract, it's a multiple times the VaR of the index. And the reason for that is that actually we should really insert this here, is that we have in here implicitly a delta of 1.0. So, right, this delta here, in this case for the futures contract, is a delta of 1.0. Okay, so here's a pretty typical FRM question from the 2012 practice exam question 1, part 1, question 1. You have been asked to estimate the VaR of an investment in Big Pharma. The company's stock is trading at USD 23 and the stock has a daily volatility of 1.5%. Using the delta normal method, the VaR at the 95% confidence level, a long position in an at-the-money put on this stock with a delta of negative 0.5 over a one-day holding period is closest to which of the following? Okay, so we're given a lot of assumptions there. But you'll notice it's an at-the-money put, and the delta of negative 0.5, that comports with intuition. The percentage delta of a put option is between, right, 0 and negative 1. So that's about right. And we're looking for the one-day holding period. So the answer there is I'm going to start here with the volatility. That's the volatility of the stock, right, which is 1.5%. And that needs to be scaled by the VaR multiple, 1.645. This is the order that I tend to think of that in. So the product of those two is the percentage VaR of the stock. But here we're multiplying by the delta because we're interested in the VaR of the put. And so that's going to be the negative 0.5 here. And then we would get a percentage there, but we're multiplying by the stock value to get a dollar amount here. And so the negative probably should be in here. I'll probably edit this to include the negative, but it's not critical because we know at the end, in terms of an answer, we're going to be expressing this as a positive anyway. But probably we should have the dollar sign here. And then I have a note about this classic FRM type question. See how it is satisfied to apply the linear approximation using only the option delta. But we do realize this is an estimate, right? So what we've done here